Welcome to the next online lecture. This lecture will be on translating into propositional logic. So the last 3 weeks, what we've done is we focused on syllogistic logic, and we looked how to assess categorical syllogisms both from the Boolean stance and from the Aristotelian stance. And that's a fairly important topic in logic and also in reasoning skills as well. And so the last couple of weeks, we're going to be focusing on what is known as propositional logic. It's basically a formalization of natural language, but a constrained formalization of natural language. So the idea is you can take arguments in your particular language and you can translate it into propositional logic, and then you can assess the statement or argument using what are called truth tables. So what we're going to learn this week is simply how to translate from natural language into propositional logic. That's what the assignment that I posted yesterday is on, okay? And then the last week, we will look at how you can assess arguments and statements using the truth table technique. So next week, we'll learn the truth table technique, and then that completes the course. So the final exam will primarily focus on categorical syllogisms and propositional logic and truth tables. So first of all, then let's look at what is called truth functional logic. So as I say here in the slide, truth functional logic, also known as propositional logic or sentential logic, was developed in the 20th century, my apologies, by Russell and Wittgenstein as an attempt to provide a logic for what they called truth functional connectives. I'll define that in a minute. Okay, so basically, we're going all the way back to the early 1900s. Russell and Whitehead published their Principia Mathematica, and then a little bit later on, around, I don't know when it was it 1912 or 1917, I'm terrible with dates, came Wittgenstein and his Tractatus Logico Philosophicus. And basically, Wittgenstein laid out a truth table technique for assessing statements and arguments in propositional logic. Okay, so that's where it all started. So this is something that has been in the books for about 150 years. Well, I'm exaggerating. We're like 125 years. Okay. So first of all, then, they were trying to provide a logic for parts of language with truth functional connectives. So what is a truth functional connective? It's any sentence function that builds complex sentences out of simpler sentences. Moreover, the truth value of the resultant complex sentence is solely a function of the truth value of the component sentences, right? So again, just to repeat, a truth functional connective gives you a more complex sentence out of simpler sentences, and the truth value of the complex sentence is completely a function of the truth values of the component sentences. And here are then the 5 main examples of truth functional connectives captured by truth functional or propositional logic. 1, conjunction. It rains and it is humid. We symbolize that in propositional logic as R and S, right? So basically, stands for it rains, and S stands for it is humid. Okay, so R and S. So the connective here, the formal connective, is the and. Okay, it rains and it's humid and. So and is a truth functional connective. The truth function of it rains and it is humid is a function of the truth value of it rains and it is humid. Another truth functional connective that is captured by propositional logic is or. And we've seen or before, right? This is the inclusive or. Remember, we distinguish between the exclusive and the inclusive or. A inclusive or B means that A could happen or B could happen or both. A exclusive or B means that A can happen or B can happen, but not both. So the sense of or that's captured in propositional logic is inclusive deduction. It rains or it is humid or both, R, wedge, S. So usually you use the little V, the vel, for or, and you use the ampersand. Some people use the dot for conjunction. Okay, the third connective that you can capture in propositional logic is called material implication. If it rains, then it is humid. So that is called an implicational statement. R, then S. All right, that's if it rains, then it is humid. And then there is material equivalence. It rains if and only if it is humid. Sorry, this didn't come out for whatever reason on the PowerPoint. That should be either a double bar or a triple bar. Okay. R if and only if S. And the last connective is not R, right? It's the negation. It rains, it doesn't rain is a negation. Notice, though, that the difference between the first four connectives and the last connective is that the first four are called binary connectives, whereas the final connective is called a unary connective. Binary connectives take two component sentences and it builds up a more complex sentences out of the components. A unary connective just takes one sentence and builds a more complex sentence out of that one sentence. So just to distinguish. So again, as I say, notice that 1 to 4 form complex sentences out of two simpler sentences. As I stated a few minutes ago, those are known as binary connectives. So and, or, if, then, and if and only if are so-called binary connectives. Whereas 5 forms a complex sentence out of one simpler sentence known as a unary connective. It just takes one sentence and gives us a more complex sentence out of the one sentence. For all 5 connectives, knowing the truth value of the component sentences completely determines what the truth value of the complex sentences. That's why we call them truth functional connectives. So just to review, for conjunction, if the component sentences are both true, then P and Q is true. Whereas if either or both are false, then P and Q is false. In other words, it's saying P and Q. So obviously both must be true for P and Q to be true. Okay? For inclusive disjunction, if either or both component sentences are true, then P or Q is true. So P or Q is false only when both are false, right? So if I'm saying either it rains or it snows and it doesn't do either, then clearly that sentence is false. But otherwise, the sentence is true. And so the sentence can be true if one or the other or both components are true. For material implication, the only case when P then Q is true is when the antecedent P is true and the consequent Q is false. Otherwise, P then Q is false. For material equivalence, P if and only if Q is true when P, Q have the same truth value. Otherwise, P if and only if Q is false. For negation, if P is true, then not P is false. And when P is false, not P is true. So what I've done here is I've given you a truth table. This is called a truth table. And again, this was invented by Ludwig Wittgenstein in his Tractatus Logico Philosophicus back in whenever it was, 1917 or something like that. But anyway, way back in the day. So if you take two simple sentences, P and Q, right, you can build complex sentences out of those using the 5 truth functional connectives. And so with P and Q, I can build the sentence not P. I can build the sentence P and Q. I can build the sentence P or Q. I can build the sentence P then Q, or I can build the sentence P if and only if Q. So basically, what you will notice is that the truth values of these complex sentences are solely functions of the truth values of the sentences that make them up. So for example, if P and Q are both true, then that's going to make not P false, right? If P is true, then not P will be the opposite, false. If P and Q are both true, that will make P and Q true, right? Because again, P and Q implies that both must be true. If P and Q are both true, P or Q can be true because the or in propositional logic is inclusive. If P is Q and true is Q, then clearly if P then Q is true. And if P and Q are both true, then clearly P is equivalent to Q will also be true. Let's look at the second rule, okay? Suppose that P is true and Q is false. Well, if P is true, that's going to make the opposite not P false, of course. Now, since one of the sentences Q is false, that's going to make P and Q false because it says both, right? If one sentence is true, that's all you need to make P or Q true. If P is true and Q is false, that's the only case when P then Q is false, all right? If P is false if P is true and Q is false, That also makes P if and only if Q false because the truth values differ. In the next column, if P is false and Q is false, and that makes not P true because Q is false. P and Q is false because one of them is false. P or Q is true because at least one of them is true. P then Q is true because for P then Q, the only case when it is false is when P is true and Q is false. And because, again, the truth values differ, then P if and only if Q is also false. Finally, let's say that P and Q are both false. Well, if P is false, that's going to make not P true. If P and Q are both false, that's clearly going to make P and Q false. If P and Q are both false, that's clearly going to make P or Q false because neither one of them is true. If P and Q are both false, that makes P then Q true automatically because the only case when P then Q is false is when P is true and Q is false. And finally, if P and Q are both false, P if and only if Q are true. So basically, to summarize, P if and only if Q is true when the truth values of the two component statements are identical. P if and only if Q is false when the truth values of the component sentences differ. So as I say here, it is important to note that the or in truth functional logic is the inclusive or and not the exclusive or. Also, there are some people regard the truth table for material implication to be counterintuitive. That is sometimes known as the paradoxes of material implication. Because some could say, well, if P is false, then how can the whole thing be true, P then Q, right? Well, one way of getting around that is to show that P then Q is equivalent to not P and not Q. In other words, it is not the case that P and not Q, right? That makes it more intuitive. For example, Jeffries, in his book on logic, argues that material implication is the weakest conditional. But in any case, it doesn't really matter, all right? Just take it on faith if necessary that in P is Q and true is Q is false, P then Q is false. By the way, you might be hearing my dog barking in the background. That's just Bubbles, okay? There are many connectives and logical operators in natural language that are not truth functional and which cannot be accounted for in sentential logic. So as I said earlier, sentential logic only captures those connectors that are regarded as truth functional, so that any complex statement built out of simple statements using those connectives, their truth value is solely a function of the truth value of the components. There are some connectives that are not truth functional. For example, believes that are necessary. If I say that it is necessary that P and P is true, I can't determine whether it is necessary that P is true or false, right? P may be true, but not necessarily true. If P is false, then I know that P can't necessarily be true if P is false. Okay. For believes that, whether P is true or P is false, that doesn't tell me whether or not I believe that P. So don't worry too much about these. The point that I'm making is that these two connectives here, necessary and believes that, necessary is a unary connective, believes that is a binary connective. Neither of those connectives are truth functional. Other examples of not truth functional connectives would be after, before, it ought to be the case that, and so forth. So as I mentioned, truth functional logic only captures the truth functional fragment of natural language. And, inclusive or, if then, and if and only if, and not. From which it follows that only natural language sentences and arguments whose main connectives are truth functional can be translated into truth functional logic. Sentences whose main connective is not truth functional are translated as additive. So if I say, I believe that it is raining, you would just translate that as A. Or it is necessary that 2 plus 2 equals 4, you just translate that as A. So the non-truth functional connectives are not translated in propositional logic. Only the truth functional connectives have a translation. So let me just go over the grammar of truth functional logic. So in a weak sense, you can regard truth functional logic or propositional logic as a very simple language. All right, it's really not strictly speaking a language, but we can say it can be regarded as a language in the weak sense of the term. Well, every language, as you know, has grammar. So if any of you have, for example, when I was in grad school, I studied both French and English. Okay, So at least on paper, I'm not actually, I'd be very hard pressed, certainly to speak German, and my French is horrible. But I mean, basically, I know the grammar of English, of French, of German. Also, when I was younger, I studied Latin. So I know actually 4 languages on paper, mind you, right? And when I remember studying those languages, and I studied Latin and French and German, what they did is they gave us the basic grammar. And using that grammar, you can build up more complex sentences, right? So it's important to understand the grammar of any language. And by extension, with truth functional language, it's important to understand the grammar of truth functional logic or propositional logic. So here I have on this slide, I have the grammar laid out. Okay. So one, any atom, A, B, C, or sentences. Now, what do I mean by an atom? I mean any sentence that doesn't contain any connectives. So for example, it rains, it snows, it is humid. None of those sentences contain any connectives, so we call them atomic. And in propositional logic, you translate atomic sentences as A, B, or C, capital A, B, or C. All right. Okay. If P is an SL sentence and so is not P. So let's say that I say it is raining. Clause 2 tells me that it is not raining is also a sentence. If P, Q are sentences, then so are P and Q, P or Q, P then Q, P if and only if Q. So the sentence in 2 is unary, and the sentences in 3 are binary. And nothing else is a TF sentence. That just means, make sure that you don't put other strings of symbols as sentences, right? So again, to summarize, the grammar of truth functional logic or propositional logic, any atom is a sentence. We symbolize atoms as A, B, or C. If P is a sentence, and so is not P. If P, Q are SL sentences, and so are P and Q, P or Q, P then Q, P if and only if Q, nothing else is a sentence. The convention of external parentheses can be dropped, although parentheses are important for complex SL sentences to avoid ambiguities. All right, so consider the following. The problem with the sentence on this slide is it's not clear whether and or if then is the main connective. So to make sure that you know which is the main connective, you insert parentheses. That disambiguates the sentence. So therefore, A and B parentheses then C, that tells you that if then is the main connective, right? A and parentheses B then C tells you that and is the main connective. So to disambiguate a sentence like A and B then C, then you need to put parentheses to disambiguate the sentence. Okay, so just for practice, which of the following are truth functional sentences? All right. Well, I have A and B and C, A or B and C. That's not a sentence because the or the and, we're not told which is the main connective. A then B, sorry, that's a sentence, right? A then P is not a sentence because P is a variable and not a constant A, B, and C. Not parentheses A then B, no parentheses, that is not a sentence because it's lacking a parentheses. A tilde B, that is not a sentence because tilde is a unary operator, and so it can't be used as a binary operator. So A tilde B is not a sentence. Now let's look at A or B and C then H. That is not a sentence because it's lacking parentheses. And A, if and only if B, then D, then C is lacking a parenthesis, so it's not a sentence. So in determining whether or not something is a sentence of propositional logic, you need to use the rules of grammar, excuse me, and you need to see where the parentheses are inserted. Okay, so hopefully we're all clear in that. So just to summarize, propositional logic captures the 5 truth functional connectives and, or in the inclusive sense, if then, if and only if, and not. Not is unary, whereas the others are binary. All right. So these are and so you can build complex sentences out of these using parentheses. Parentheses disambiguate the sentence so we know which is the main connective. All right. And so that's what we've done so far. Now, the main task for this week and the task on your assignment is to, the main task in your assignment this week is to be able to translate from natural language into propositional logic. Okay. There are exercises in the Vaughan text that I've posted on the website. And then I have posted a short assignment. I think I have 8 translations altogether. So whatever it is, I forget now how many I put on. And anyway, you work through all of those, and then that will give you good practice translating from natural language to propositional logic. Okay. Now, before we get into the actual translation business, there are some important idioms that should be noted before attempting translations into sentential logic. So what I have, like if you've ever studied languages, like when I studied French, there were all kinds of idiomatic expressions, right? And I think yeah, that should be okay. I'm right there. Sorry, I'm just responding to a text. My apologies, man. Sorry about that. My apologies. I should have really put the phone off. But anyway, I'm sorry about that. Okay, so preliminaries to translating into SL from natural language. There's some important idioms that we need to know. First of all, P only if Q. Okay, so P only if Q. It can be translated as P, then Q. All right. So just keep that in mind. Know all of these idiomatic expressions, and that will help you to translate into propositional logic. As I was saying earlier, for natural languages, when I learned French and German and so forth, we learned idiomatic expressions, right? And that's important for translating into the requisite language. So P only if Q is P arrow Q, P then Q. P if Q is Q arrow P. So keep that in mind. Only if you preserve the order P arrow Q. If P if Q, you reverse the order, it's Q then P. All right. P is necessary for Q. Sorry for the typo there. That should be Q then P, right? P, the necessary condition is always the consequent of the conditional. P, uh, P then Q. P is sufficient for Q. All right. Um, P on the condition that Q, Q then P. P provided that Q, Q then P. P just in case Q is just P if and only if Q. All right. P unless Q is P or Q. P but although Q um, is P and Q. P or Q but not both. This is the exclusive or. So remember that sentential logic, the propositional logic, covers both kinds of, covers truth functional connectives. And it doesn't cover the exclusive or, it only covers the inclusive or. So P or Q, but not both, is P wedge Q, parentheses, and not P and Q. So see what this intuitively means here. It means P or Q, but not both P and Q. So that's the exclusive or. Neither P nor Q. That can be either not P or Q, P parenthesis or Q, or it can be not P and not Q. That's the application of what are called De Morgan's rules. We'll talk about those maybe next week. Okay. Um, so P but although Q, okay, sorry, I just covered that. P or Q, but not both. Again, that's exclusive or P or Q, but not both. We already went over that. Sorry for the redundancy. Neither P nor Q. That means P doesn't happen and Q doesn't happen. You can translate it as either not parentheses P or Q, or you can translate it as not P and not Q. Those are called De Morgan's rules. Okay, not both P and Q. Then you can have not parentheses P and Q, that says not both, or you can have not P or not Q, which means either P must be false or Q must be false. Again, these equivalences are known as De Morgan's rules. So why don't we just review it one more time? All right, nothing wrong with review. So again, if you look at these idioms, okay, P only if Q is always translated as P then Q. All right, P if Q is always translated as Q then P. P is necessary for Q. Typo again, my apologies. It should be Q then P. The P is necessary condition. It's always the consequent of the conditional. P is sufficient for Q. P is always the antecedent of the conditional, P then Q. P on the condition that Q is again Q then P. If Q then P. P provided that Q, Q then P. P just in case Q is the same as P if and only if Q. So P, equivalence Q. P unless Q, unless is typically translated as or, P or Q. P but, although Q, is P and Q. P or Q, but not both, that's the exclusive or. P or Q and not both P and Q. Neither P nor Q. This is, you could say tilde P wedge Q, or you could say not P and not Q. Those are equivalent. Those are called De Morgan's rules. Not both P and Q, you can say tilde, parentheses P and Q, not both, or you can say not P or not Q. Those are called De Morgan's rules. So these are the idiomatic expressions you can translate into. So this will help us when we do actual translations from natural language into propositional logic. So what I want to do now with you is to give you a strategy for translating from natural language to propositional logic. Hi, Bubbles. Okay, step number 1, identifying the main connective using syntactic markers like commas and semicolons. Step 2, is the main connective truth? So is the main connective truth functional? If no, then translate it as an atom. If yes, proceed to step 3. Translate the connective into truth functional logic, placing parentheses around components. Translate the atoms into letters and the remaining connectives into SL. Step 5, repeat step 3 for the component sentences, inserting parentheses where needed. I know this is kind of abstract, but let's look at some actual examples. So here's an actual example. It rains only if it snows, comma, unless John believes that it is humid or cloudy. So remember, this says here, step 1, identify the main connective using syntactic markers such as commas and semicolons. Well, the syntactic marker in this sentence is the comma, right? It rains only if it snows, comma, unless John believes that it is humid. So the comma, what the comma tells you is that the unless is going to be the main connective, all right? That's going to be the main connective. So what is the main connective? Step 1, unless. And we translate it into a nor, right? So step 2, is the main connective truth functional? Yes. It's unless is translated as or, wedge. Step 3, we now translate the main connective. So it rains only if it snows, wedge. John believes that it is humid or cloudy. Now what we have to do is to translate the components. It rains only if it snows. John believes it's humid or cloudy. Well, it rains only if it snows is going back to the idioms is P then Q, right? So it will be then, it rains only if it snows, so it'll be R then S. Wedge. John believes that it is humid or cloudy. Since believes that is the main connective here, then it's just going to be translated as atomic letter because you can't render believes that in simple propositional logic. So step 5 gives us R then S, wedge A. Okay, let's go over that one more time. So how do I, using these steps, how do I translate it rains only if it snows, comma, unless John believes it is humid? Step 1, what is the main connective? Unless. How do I know that? Because of the syntactic marker, comma. Step 2, is the main connective truth functional? Yes, unless is typically rendered as wedge or in propositional logic. So what I do then is in step 3, I translate the main connective and then I put everything else in parentheses. Step 4, I translate it rains only if it snows according to the idiom, such as R then S. Now all that I have to translate is John believes that H or C. Well, the thing is is it believes that is the main connective, and that's always translated as atomic litter. So we get R parentheses, R then S parentheses or A. So let's try some elementary translations into SL or PL together, okay? So either it rains or it snows, comma, unless it is neither humid nor cloudy. So we know then that unless is the main connective because of the comma, right? Okay. We know then that it rains or it snows unless it is neither humid nor cloudy, unless it's the main connective. Further, it rains or it snows is just R wedge S. Neither humid nor cloudy would be tilde H or C, or if you want, not H and not C. Either it rains or it snows unless it is neither humid nor cloudy. Let's look at, sorry about the lettering is a little mixed up there, my apologies. Let's look at it's raining is either a necessary or a sufficient conditioning for it snowing. So that means then that either S then R or R then S, right? So raining is a necessary condition would be S then R. Raining as a sufficient condition would be R then S, and we connect those two using a NOR. Here's number C. It's raining is neither a necessary nor a sufficient condition for it snowing. Then, first of all, you take a necessary condition, that would be S then R, sufficient condition R then S, and then you negate both of them because you're saying it's not the case that it's raining is necessary, and it's not the case that raining is sufficient. Unless it is humid, it will either rain nor snow. So the comma tells you that unless is your main connective. We know that unless in propositional logic is translated as a wedge or a nor. It will neither rain nor snow, not R or S, or if you want, H or not R and not S. That's using De Morgan's. Only if it rains will it snow, which means it snows only if it rains, S then R. If, but not only if it rains, it will snow. So if it rains, it will snow is R then S, and it is not the case that it rains, it snows only if it rains, not S then R. So these are some translations into propositional logic. And this is what I want you to do for me on the next exercise. I'm not going to give any truth tables on the exercise, just translations from natural language to propositional logic. A few more. A necessary but not a sufficient condition for it snowing is humid. So remember, necessary condition is the consequent of the conditional. Sufficient condition is the antecedent. So if I'm saying that it's being humid is necessary for it snowing, that would be S then R. But I'm also saying that it's not a sufficient condition. Well, H being a sufficient condition for S would be H then S, but because it's not a sufficient condition, then it's not H then S. So S then H and not H then S. It's raining implies or is implied by its being humid. This is it, so it's raining implies it's being humid would simply be R then H. It's raining is implied by its being humid would be H then R, and I can join those by or. That's the main connective. And finally, it's raining implies or is implied by it's not snowing, but not both. Okay, so that's the most complicated one of the bunch. So let's take a look at this. So it's raining implies it is not, implies or is implied by it is not snowing, all right, by it's, but not both, okay? So therefore, and actually there should be a not in there, but anyway, it's okay. So R then S or S then R. So it's raining implies or is implied by it's not snowing. So that should really be R then not S or not S then R. But not both. But it is not the case that both. So then it would be not R then not S and not S then R. Okay. So I'll give you a few like these on your translations. These are kind of quantity expressions. These are the precursors to what are called quantifiers in predicate logic. In this course, we won't have time to get to predicate logic. So let's look at some additional translations. So what I will typically do is I'll give you a symbol key. So A means team E wins. B is atomic. It means team B wins. And C is atomic. It means team C wins. So first of all the teams win. You agree it would be A and B and C, right? All three teams win, A and B and C. At least one team wins, well, either A wins or B wins or C wins, right? At least one team wins, A or B or C. Exactly one team wins. That means A wins and the other two don't. Or it means that B wins and the other two don't. Or it means that C wins and the other two don't. And so it looks long and convoluted, but that's all it's saying. To say exactly one team wins means that either A wins and the other two don't, or B wins and the other two don't, or C wins and the other two don't. At most, one team wins. So that means that either A and B lose, right? Or B and C lose, or A and C lose. And that guarantees that at most, by the way, all three can be true. It isn't the case that one team wins. It's just that at most one team wins. Now, if I say at least two teams win, then either A and B win, right? Or B and C win, or A and C wins. At most two teams win means that at least one of them must lose. So not A, or not B, or not C. Okay, so with today's lecture and the corresponding PowerPoint, you should easily be able to translate from natural language to propositional logic, and that is your assignment, and the suggested exercises involve the same kind of task. Okay, so we will talk to you next week. Thank you.